NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman Lecture Series. Now, I had a teacher in college who on the very first day, he drew a tiny little circle on the whiteboard. And he said, "This is everything that you know." Now, being college students, we were a little insulted by him implying that we only knew a little bit of knowledge. But he said, "It's okay because everything that circle is touching is everything you know you don't know." He said by the end of the class, he drew this much bigger circle all the way around it. And he said, "I hope this is you. And I hope that everything that that bigger circle is touching is everything you now know you don't know." Tonight we'll be discussing the Jupiter system and the many mysteries that it has unveiled to us. You're going to hear some very smart people tonight say, "I don't know." But I want you to remember that's where discovery begins. Now, joining us as co-host, fielding your questions this evening, is Public Outreach Specialist Lindsay Mclaurin. Hiya, Lindsay.
Hi, Brian. Thank you so much for having me join you tonight. And to everyone at home, we just want to remind you that this is your space program, and we want you to be a part of the conversation tonight. So from wherever you're joining us, please use the chat function to ask us questions, and a member of our amazing social media team will pass them along to us. We'll try to get through as many questions as possible, but if for some reason you don't see the chat, please refresh the page and it should be up shortly. Let's get started, Brian.
Thank you, Lindsay. Let's get started. As a reminder, folks, if we run into any technical difficulties, we ask that you do stick with us as we get those sorted out. Now, our first speaker is the Juno project scientist and the lead co-investigator for Juno's microwave radiometer instrument. He has worked at the Jet Propulsion Laboratory since 1990. His research interests are many, but he is also currently the lead scientist for the Goldstone Apple Valley Radio Telescope Project, GAVRT, in which students learn about science by doing real science. Please welcome Dr. Stephen Levin.
Hi, nice to be here.
Welcome. Well, let's get started. Let's get started with your JPL origin story, how you got to where you are today.
Sure. Well, I talk to school kids all the time, and they always ask that question. So I have kind of a pat answer for it. And the truth is, I became a scientist because I have a bad memory. So when I was a kid in school, and there's tests and whatever, I had trouble remembering what the teacher told me. But I quickly learned that I could figure out the answer instead. And by doing that, I learned, hey, figuring out stuff is fun. And it also turns out that figuring things out is what scientists really do. So that's kind of how I became a scientist. And pretty much all of my career choices about what kind of science have been made on the very careful basis of, that sounds like fun. So that's what I've been doing.
Well, it sounds like you've been doing more than that. I imagine the project that you're working on then is a lot of fun. So talk to us a little bit about Juno and what it is.
Sure. And I see we've got a slide up there with a little summary. So Juno is our spacecraft that's orbiting Jupiter, and we've been there since 2016. And the slide here is a little overview. I'm not going to read everything on the slide, although I'll point out that we flew by Ganymede last week and changed our orbital period. So that 53-day polar orbit it says in the middle is now a 43-day polar orbit. But in that time, what we've been trying to do is understand the origin, the interior, the atmosphere, the magnetosphere of the solar system's largest planet. And we have an extended mission approved by NASA, so that starts in August, and we'll fly by other satellites, and we'll get closer-up data of the North Pole of Jupiter, and keep on going. And I guess that means now's a good time to talk about all the cool stuff we've learned so far.
Well, I think so, but you also had a pretty exciting day this past week and a half, right?
Sure. We had a Juno science team meeting this week, and we had a flyby of Ganymede last Monday. And so we have all kinds of cool stuff. And yeah, here's a great new picture of Ganymede that we took with Ganymede's first close-up in about, I don't know, a generation, 25 years or so. We have lots more to come, but we only had the data about a week, and we're still trying to understand things and analyze it. So you can find tons of pretty pictures from the flyby on the Mission Juno website. And there'll be lots more science results on Ganymede. We looked at Ganymede in a new way, as well as just for the first time in a long time. And we'll have lots of science results for that, but not today, because a week is way too fast to be sure that we're right about pretty much anything we say about the science results.
Well, that's
All
a
right.
good...
So
That's a great segue,
Okay.
though, because you just said before we know we're right about things. This mission, you've told me when we were talking about this, has surprised you in many ways.
Yes. And in fact, why don't we switch to that next slide, which is there's a way more than 10. There's so many new discoveries and surprises that, I couldn't make one list. I couldn't make one talk that was just about the most exciting discoveries. But the short version is it's a whole new Jupiter. I love that quote from Mike Jansen, one of our scientists, when we first started getting data on Jupiter and finding out that all our ideas were wrong. So basically, Juno has measured Jupiter in a bunch of new ways. And pretty much every time we did a measurement in a way that hadn't been done before, we found that our ideas about what we were going to see were just wrong. We got surprises, which is a lot of fun. If you're an experimentalist like me, you like, getting the new data and making all the theorists start over. So I'll tell you a few of them out of this list. I'm not even going to try to read the list of top 10, but I'll tell you a couple of my favorites. One of them is the deep atmosphere is not well mixed. So what that means is, Jupiter's this giant ball of gas, right? And what everybody thought before we sent Juno there to try to look below the clouds was if you got deep enough below where the sun shines in Jupiter and below where the clouds form, it's all gas. It's all fluid. It would be well mixed, and you'd find pretty much anywhere on the planet looked about the same. And when you look through at depth, it would make sense. It would be smoothly varying and things. And well, that was totally wrong. What we found is all kinds of structure with our microwave radiometer that can see beneath the clouds, all the way down to several hundred kilometers, as deep as we can see, we see structure. So that was really cool. Gives us all kinds of puzzles and things to try to figure out. Some of the other things we found were the core in the middle is extended, it's dilute, it's fuzzy. So we all knew that there ought to be down in the center of Jupiter some kind of core where the heavy elements sank to the middle of the planet, right? If it's all fluid, all the heavy stuff should be down there at the bottom. And people kind of expected a sharply delineated core down in the middle, maybe not a solid core, but 3 to 5, maybe 10 times the mass of the Earth, maybe even 20 times the mass of the Earth, but mostly way down in the center. And what we think we found with the gravity is, yeah, that stuff is there, but it's way up higher. It's spread out and diluted up to half or maybe even 3/4 of the radius of the planet. So that's really strange. And now one of the things we're trying to figure out is there an even denser core down in the middle that is separated? There's a lot new data to be collected and a lot of puzzles to try to solve. I'll pick out another one of these is the magnetic field. When we first got our look at the magnetic field of Jupiter, we found it was more complicated than we expected. And we now know that it's asymmetric. The north part of Jupiter has a much more structured, complicated magnetic field than the south part of Jupiter. Now, we knew before we got there that Jupiter had the largest magnetic field of any planet in the solar system. And we expected it's caused by swirling motions in the ocean of liquid metallic hydrogen deep inside the planet. So hydrogen gas squeezed by gravity so much that it conducts electricity and it can make a magnetic field. But what we didn't expect was all the structure that we see, because even though we're getting this close-up view of the magnetic field, we're not getting any closer than the surface of the planet. And so we're seeing it still from a distance. And the only way we can see that much structure is if something is going on at a shallower place than where we thought the magnetic field was generated. So that's pretty exciting. And then, of course, all this asymmetry is really strange, that it's got all this complication in the north, and it looks kind of smooth and a lot more like a regular Earth-type dipole in the south. So that's another mystery. I could go on and talk about all of these and use up all the time, but I really want to talk about whatever people want me to talk about. So what I'm hoping to do is stop right here with me telling you and let people ask questions, and I can answer whatever anybody asks, even if the answer is I don't know.
Well, let's find out what they are asking online. Remember, if you don't see the chat, refresh, and you can get that popping up. But Lindsay, what are they saying out there?
Steve, the folks in the chat are super excited about talking about Jupiter. And so one of the questions Chris wants to know on YouTube, what is the atmosphere like on Jupiter?
Okay, so Jupiter is mostly hydrogen and helium, right? So hydrogen is the lightest element there is. Here on Earth, it would float up into the sky. But Jupiter is so massive, 300 times the mass of the Earth, that the pressure is so high that you don't have to get very far into the planet, very far below the cloud tops, to get to a region where that hydrogen is compressed to something much different from what we experience here on the Earth. If you get a quarter or a third of the way in to the planet, it's squeezed so much it's a liquid. It can even be squeezed so much it conducts electricity. It's a liquid metal. So that's just the hydrogen. Now that's way down in. At the top of the planet, the top of the atmosphere, there's still hydrogen. There's helium is the next most abundant. Then there's ammonia. So the nitrogen there is bound up with the hydrogen. NH3 makes ammonia. So you have a lot of ammonia in Jupiter's atmosphere. You have methane. You have lots of different chemicals now because way up at the top of the atmosphere, it's less dense. It's not squeezed the same way, and it can let the sunlight in. And the sunlight causes all kinds of chemical reactions to happen. And then it circulates because Jupiter's hot down in the middle and cold up at the top. So we've got a wide range of different elements and different chemicals, different chemical compounds. I don't know, that's probably more than you wanted to hear me say. But it's a pretty complicated atmosphere, and we can use some of what we learned at Jupiter to try to understand more about the Earth and vice versa.
Thanks, Steve. Anthony on LinkedIn is asking, is Jupiter a gas giant that will be dangerous for the long-term future of planet Earth?
So Jupiter is certainly a gas giant. I don't think I would say it's dangerous for the long-term future of planet Earth. In fact, I'd say maybe Jupiter, you should think of Jupiter like kind of a big brother that protects us. Now, it's a little bit of a two-edged sword, but if you imagine something falling into the inner solar system like a distant comet, as it comes into the inner solar system, it's going to interact most likely with Jupiter before it interacts with the Earth or with the other planets, because Jupiter is further out and it's way more massive. And most of the ways in which something falling into the inner solar system could gravitationally interact with Jupiter would result in kicking it out away from the inner solar system, so it'd be less likely to hit the Earth. Now, that's not the whole story. Jupiter's got this enormous gravity. It can also perturb the orbits of things, and I won't promise that Jupiter's gravity couldn't perturb some comet and have it result in hitting the Earth instead of avoiding the Earth. But on balance, I'd say Jupiter is more protective than it is dangerous to us. And of course, it's really far away, so you don't have to worry about like Jupiter's gravity affecting the Earth in any major way.
Dimitri on Twitter would like to know, why are there such distinct colored storm rings around the equator of Jupiter?
Yeah, great question. So we call those the belts and zones. And if you look at a map of Jupiter, let's see. Actually, I think we have one of those backup slides shows. Let's see if I can find it. It's too hard to look through all these pictures and find the right one. But if you see one that's shows the depth of the belts and zones, you could put it up. So what's happening? Those things are jet streams. So we've known for a long time, because we can watch them from the Earth in the upper atmosphere, that they move relative to the rest of the planet left and right. So if you go back and forth from those stripes, from the orange to the white to the orange to the white, as the alternating stripes you see on Jupiter, some of them move to the left and some of them move to the right. Not the picture I had in mind, but we can use it. If you look at that picture and ignore the magnetic field that's drawn on in blue and red, you can still see the belts and zones as in this case, white and dark stripes. So they move in alternating directions. What we didn't know until Juno got there was how deep those things go. Now we know if you have a rapidly rotating planet, and Jupiter rotates pretty rapidly every 10 hours, so more than twice as fast as the Earth. And it's giant, right? It's 300 times the mass of the Earth, more than 1,000 times the volume. So rotating that fast means it's really going to affect the motions of the fluid. And because it's a fluid most of the way down, maybe all the way down, we knew that doing that would tend to result in back and forth jets like that. What we didn't know is how deep they go. Juno's been able to measure that and found they go 3,000 kilometers down into the planet. So understanding how that works is complicated, but we can do experiments where you spin things or spin fluids around and watch what happens. We can do numerical experiments where you try to calculate what happens. And the combination of the heat in the middle trying to escape that causes convection, and the rotation of the planet that gives you things like the Coriolis effect results in upwelling has to spread out, and when it spreads out, the part that spreads out goes in opposite directions. So if you think about something rising near the equator, and say if it rises near the equator and goes a little bit north, what happens? Well, if it's right there at the equator and it goes a little bit north, now to keep up with the rotating planet, it doesn't have to go quite as fast as it did in the place where it rose. If you go a little bit south, same thing happens. So you'd expect at the equator to have, if air is rising, to have it move at slightly different speeds at the equator than it does north of it or south of it. And if you do it again with an X stripe and figure that out, you wind up concluding that, yeah, it sort of makes sense to have all these stripes go back and forth in opposite directions if I have air upwelling and falling back down into the planet.
And if you bring up image 20, I think we can see a little bit of a chart that he was talking about.
Yeah, sorry, it was hard for me to keep track of.
No, you're the expert, yeah.
Yep, here it is. Right. Okay, so what you're seeing there, the zonal winds, that's the speed of those jet streams, right? Plotted, that's the squiggly line. And it's plotted on top of an image of Jupiter, so you can see how the winds match up with those belts and zones with the different colors, which are different chemicals in the very top of the atmosphere. And then what Juno has added to that is our gravity signature, as Juno flew really close to Jupiter, very close. We fly about a 20th of the radius of Jupiter away from it, so just skimming above the cloud tops. As the spacecraft flies really close to Jupiter, gravity from the planet makes it speed up and slow down. Not just the gravity from the whole thing, but from stuff that's close to us. If you imagine, if you flew over something that's a little denser, as you approach it, you're going to speed up a little. And as you pass it, you're going to start slowing down a little. So by measuring all of those things in great detail, we can figure out, among other things, how deep those belts and zones go. And the answer is they go quite deep. 3,000 kilometers is a lot deeper than many people thought we were going to find. That's probably enough.
Thanks,
on
Steve.
The for a while, huh?
We can talk about that forever. Jupiter is just so beautiful and amazing. And so Gustav on Twitter wants to know, why are some of the moons of Jupiter still unnamed?
I don't know. I'm only guessing, but I would guess that the starting point there is you got to decide what's a moon and what's just a rock, right? So really big objects orbiting Jupiter, pretty obvious. We get to call them moons. They've been discovered a long time ago, and they all have names. Some of them have names from things we've seen from the Earth. But as you start getting smaller, then when you start into getting the objects we haven't discovered yet, then those are fairly small. And I'm only guessing, but I would guess they don't have names yet because either they're fairly new or because there's some debate as to whether it's big enough to deserve a name as opposed to a number. But as I say, the truth is, I have no idea. I wasn't even really, until you asked the question, aware that was a thing, that there's a bunch of moons of Jupiter that aren't named. And I'm guessing they're smallish rocks.
I loved the first I don't know of the night, but that's also a great transition question as we pass it over to our next speaker. Steve, Lindsay, will come back to you with questions in just a little bit, but we're going to move on to our planetary geologist at JPL who specializes in surface processes on icy airless bodies. She is a project staff scientist and science communications lead on the Europa Clipper mission. Dr. Phillips has an undergraduate degree in astrophysics from Harvard and a PhD in planetary science from the University of Arizona. Welcome, Dr. Cynthia Phillips. Hi.
Hi, thank you so much. It's fabulous to be here. And thanks to
Th-
Steve for telling us about all the amazing stuff that we've been learning about Jupiter.
Well, I'll let you ask him some questions here in a bit, but I want to get your origin story. We got Steve's. I want to hear how you got to where you are today.
Sure, yeah. So my origin story really relates back to the power of I don't know. I was in high school when the Voyager spacecraft flew past Neptune. And, I was a persuasive kid, and this is pre-internet. And so the way that the team on the Voyager spacecraft, the camera team, was able to see the pictures that were coming of Neptune and of its moons for the very first time was they actually had to go to JPL, and they went to the control room and they sat there and they watched as the pictures came in on these big monitors up in the control room. And so PBS, this is, there's no internet, right? So if I wanted to see the pictures, you had to wait for them to be published in the newspaper or something like that. It took forever. So PBS had a live stream from the JPL control room. It was called Neptune All Night, and they basically just had it on all night. And I was a persuasive kid, and so I remember I persuaded my parents to let me stay up all night and watch this thing. And I remember it's the middle of the night, and there's Carl Sagan, who of course was on the camera team, and this picture comes up of one of the moons, and Carl Sagan looks at it and he says, "Wow, I have no idea what that is." And it struck me in that moment as a high school student that there are still places in the solar system that are yet to be discovered. There's places that human eyes had not yet seen before. And that just gripped me, that there was so much that, we were at the cusp of discovering, and I wanted to be part of that.
Well, you're a big part of it now. So what gripped you about Europa? Why Europa? Why is that a place we're looking at?
So Europa is this moon of Jupiter, and it does have a name. It's one of the big ones. So it's one of the four Galilean satellites. And what's special about Europa is that it's about the same size as Earth's moon. But as you can see in this picture, it looks really different. Instead of having a surface that's covered over with craters, instead of being an old kind of battered rocky body like our own moon is, Europa is covered with ice. And we think that Europa could actually have what we call the planetary ingredients for life. And so those are things like liquid water, a source of energy, and the right chemical elements for life. So that's things like carbon, hydrogen, nitrogen, phosphorus, sulfur, and then as well as stability. It's no good to have these ingredients there if you don't have enough time for chemical reactions to take place that maybe could lead to life. And the really cool thing about Europa is that we think it's one of the best places to look for life beyond the Earth because it has all of these ingredients. So if you can go to the next slide, Europa's surface, so again, it's a really young surface. It has very few craters. You can see there's one kind of nice big crater there in the bottom left of that grid on the right-hand side there. And it's a young crater. And you can see these bright rays of material that have spewed out in all directions from it. But most of the surface is covered with these long linear features called cracks and ridges that extend for thousands of kilometers across the surface. And then there's places where the surface has been broken up into what look kind of like icebergs. And these are places where the surface has kind of broken up into pieces. It's rotated, it's translated, it's even tilted, and then it looks like it froze into these new positions on the surface. And while these look like icebergs, they're many, many times bigger than any icebergs we have here on Earth. So the Titanic wouldn't stand a chance if it was there. And then we have other features that were just strange looking, these little lenticulae, and these are little sort of dark spots on the surface. And all of these features, plus other evidence that we got from the Galileo spacecraft, that was a spacecraft that was in the Jupiter system in the 1990s, and that I was fortunate enough to get to work on when I was in graduate school. The Galileo spacecraft took all these images, it took information from all of its other instruments, and it suggested very strongly that underneath this icy layer at the surface, there's an ocean of liquid water, and that this ocean could have more water than all of Earth's oceans combined. And if you go to the next slide, basically, it's really exciting to think that there could be an ocean here so far away from the sun. And this really revolutionized our thinking about the habitable zone, about places in the solar system that could be inhabited by life. And again, this is life as we know it. There's also some crazy, strange life in Star Trek that maybe we haven't figured out yet. But, when we're looking at life, we just have to do the best job we can. And that means until someone builds me a tricorder, it's going to be life like we have here on Earth. that needs those ingredients that I talked about. And so here on Europa, we think that there could be this big ocean layer of liquid water, and we think it could be kept liquid by what's called tidal heating. So basically what happens is that Europa goes around Jupiter, and it has about a 3.5-day orbit. And as it goes around, sometimes it's closer to Jupiter and sometimes it's further away. When it's closer, remember Jupiter is, it's the biggest planet in our solar system, actually has more mass than all of the rest of the solar system, except for the sun, combined together. So Jupiter's huge. Its gravitational forces are massive. And so when Europa is a little bit closer to Jupiter, its surface gets tugged on, it gets stretched and pulled and elongated a little bit. And then when it moves around in its orbit, so it's further away, surface goes down. And it's this stretching and pulling as it kind of gets squished. That's what we think generates frictional heating. This is called tidal heating. And it's that friction, that tidal heating, that keeps this liquid water ocean liquid. And we think this ocean could have been there over the age of the solar system. So 4.5 billion years, this ocean has been sitting there simmering. And so because of this, because of these discoveries made by the Galileo mission back in the 1990s, NASA's been working on a new mission called Europa Clipper. And so in the next slide, please, Europa Clipper will basically explore Europa to investigate its habitability. And it has a payload of a bunch of different instruments shown here. The ones that are circled in blue are what we call our remote sensing instruments. And so that includes things like an ultraviolet spectrometer, there's an imaging system, there's a near-infrared mapping spectrometer, there's a thermal imager, and there's a radar instrument. And these instruments will all let us study the surface, but some of them will actually be able to penetrate into the subsurface. That reason ice-penetrating radar will be able to go through the subsurface ice layer, go through the surface ice layer down into the subsurface. And depending on how thick the ice layer is, we know there's a layer about 100 kilometers or so thick at the surface. Some of that layer is frozen solid ice, some of it's liquid water. We're not sure yet how much is frozen and how much is liquid. The reason instrument maybe will be able to help us determine how thick that ice layer is. And it'll also be able to look for places within the ice layer where there could be inclusions, so pockets of liquid water. And then we have another set of instruments that we call our in situ instruments. And so these are a mass spectrometer, there's a dust detector, there's a magnetometer, and there's a plasma instrument. And so these instruments will let us sample the composition of Europa. And these don't do it directly, so we're not gonna land on the surface of Europa, not with this mission. But what the mass spectrometer and the dust analyzer do is it's kind of like Europa Clipper sticking out its tongue when it goes by Europa, and it's capturing some of that material that's thrown off the surface. And so if there's a plume erupting on Europa, now this is possible. We've seen plumes erupting from the tiny little moon Enceladus that orbits Saturn. So we think maybe there could be plumes on Europa. We haven't seen them yet, but if we do find a plume, we'll be able to fly through it, probably with the Europa Clipper spacecraft, and sample that material directly. But even if we don't find a plume on Europa, there's still enough material that's just thrown off the surface due to impacts from Jupiter's very strong magnetic field that accelerates charged particles into the surface. Those impact the surface and they send off material out into space. They make this very, very thin, tenuous atmosphere. And as the Europa Clipper spacecraft flies by Europa on its multiple close approaches, it'll be able to sample that material and determine its composition. And then finally, we have a magnetometer and a plasma instrument that will be able to tell us more about the space environment surrounding Europa, and also maybe help us determine exactly how thick that ocean layer is by looking for an induced magnetic field signal.
Yeah. If we go to the video next, we can see that plume. You're right, that you're talking about.
Great. Yeah, so Europa Clipper it's a spacecraft that rather than orbiting Europa, the problem is that there's so much radiation around Europa that we can only survive for a matter of weeks in Europa orbit. But instead, we'll have multiple close flybys from Jupiter orbit of Europa. And so here's just an artist's conception where if there is a plume actually erupting from Europa, we'll be able to fly right through it and sample it. And that would just be spectacular. But even if there isn't a plume, we'll still get just amazing results from Europa Clipper. So the spacecraft will have multiple close flybys, 50 or so, of Europa over the course of a couple of years in the Jupiter system. And so we're really looking forward to these new results from Europa Clipper. So stay tuned.
Very cool. Lindsay, I know there were a lot of questions about Jupiter. I imagine there's a lot of questions about Europa out there too.
You are absolutely right, Brian. So Cynthia Irvin on LinkedIn is asking, how many instruments are flying on Europa Clipper? Is there an instrument that hasn't flown before or is very specific to Europa?
Sure. So if we can go back 2 slides to the list of instruments. Sorry, forward 1, 2 more. Yeah, this one. Okay, so there's a bunch of different instruments on Europa Clipper. It depends on how you count them, whether or not there's 9 instruments or 10, and that's because the camera on Europa Clipper, there's a narrow angle camera and a wide angle camera. So sometimes we count those as 2 different instruments because, technically it is 2 separate cameras, but they're both part of the ICE Europa imaging system. So we've flown some of these instruments to Europa before, and some we haven't. Some of the ones that are really special here are the Reason, the ice penetrating radar. That's a new instrument, and we've been using instruments like this on Mars to look below the ice sheets in the poles of Mars. And we also use instruments like this on the Earth to study ice sheets on Earth. And so this technology of an ice penetrating radar, it's been tested on Mars, it's been tested on the Earth, but this will be the first time that we're sending an instrument like this to the outer solar system. So I'd say that the Reason instrument is one that we're all really excited to see what it looks like. And then another one that I'm also really excited about is actually the ultraviolet spectrograph. So this is the Europa UVS instrument. The Galileo spacecraft that we got most of our information from about Europa so far did not have an ultraviolet instrument. And so we had a camera on Galileo that went down into about the violet range. But I'm really excited to see, we can look for an aurora, and we can look for the ultraviolet spectrograph might also be useful to look for plumes. And so this will also be a really exciting sort of new instrument that we'll be taking with us to the Jupiter system.
Thanks, Cynthia. Crimsy on YouTube would like to know, how deep is the ocean on Europa, and how much does that depth vary?
That's a great question. Let's see if we can go back 1 slide, please. So this image actually shows that basically Europa's ocean, so the layer at the surface, that's about 100 kilometers thick or so. It's 100 kilometers, maybe plus or minus like 30 or something. So you'll see you hear people talking about, it's an ocean about 100 kilometers thick, maybe with like 30 kilometers of ice on top of it. The truth is that, again, this is an I don't know, but it's not quite as unbounded as some of our I don't knows. We do know that there definitely is a layer at the surface of Europa that has the density of water. The problem is that the density of solid water ice and the density of liquid water are really close to each other. And so the gravity measurements from the Galileo spacecraft that we used to detect this layer, they just weren't good enough to distinguish between how much is solid ice and how much is liquid water. So most of the best estimates we would say are that it's about 100 kilometers or so of water, maybe 80 kilometers of water, and then maybe 30 or so kilometers of ice on top. Likely there is some variation, but probably not a whole lot. Like there probably aren't huge sort of like, big pointy icebergy things that are places where the ice shell is really jagged at the bottom of the ice shell. And that's just because if there are places where there's a lot of topography at the bottom of the ice shell, so at the top of the ocean, probably the currents in the ocean and just the temperature would kind of smooth those out pretty quickly.
Well, let's bring Steve back in here. There are a lot of questions in this chat tonight, and I've only heard I don't know a couple times, and that's pretty great. You both talked to me early about how proud you are when you get to say that answer to a question. Lindsay, we got time for just a few more questions from our audience.
Absolutely. So Steve, this question I think you can answer. Darren on Facebook would like to know, could the public possibly be allowed to give naming suggestions for Jupiter's unnamed moons?
Way above my pay grade. So I don't know. I'm sure there is a protocol for deciding how to name moons of other planets, but I don't happen to know what it is.
I can talk about that a
Maybe.
little bit, Steve, actually. So I've worked a little bit I've worked a little bit on planetary nomenclature, actually. And so it really depends on what sort of feature what sort of object we're talking about. And so a moon has to fit into certain naming categories. And so the moons of Jupiter mostly come from, Greek mythology. There's some other sort of special cases depending on sort of different clusters of moons. But we have done there have been cases in the past when new moons have been discovered. You can't name a moon after a person, right? The International Astronomical Union has very sort of strict requirements on this. But the person who discovers a moon does actually usually get to suggest a name to the International Astronomical Union. And if that name kind of follows within the naming conventions, then sometimes that name can be adopted. And so, yeah, sometimes in the past there have been sort of name a moon, sort of not really contests, but sort of public, periods where basically it's been open to the public to sort of suggest names and then help vote on names. But the public doesn't actually get to officially name any of these moons. So stay tuned.
Thanks, Cynthia. Lainey is asking a question for her daughter, Sloan, who would like to know why there are geysers on Europa.
That's a very good question. So first, we don't know whether or not there are geysers on Europa. I really like there to be geysers on Europa, just because I think that would be super, super cool if Europa was actually ejecting material out into space, like this big sort of like space, eruption. And we do see those on Saturn's moon Enceladus. And so we know that it's possible, right? If Enceladus can do it, come on, Europa's got to be able to do it too. Part of the problem with Europa is that it's a lot bigger than Enceladus. So just because we see plumes that are actually being vented off of Enceladus, if plumes did exist on Europa, they'd be a lot smaller. So they wouldn't be quite as spectacular as these kind of giant jets of gas and dust that we see coming off of Enceladus. But if there are plumes, that would be really fascinating, because basically that would mean that somehow the liquid water ocean of Europa made it up close enough to the surface that it was able to erupt and sort of make it out into space. And so, again, we're not really sure how that could happen, but we think it could. But we won't know for sure until we go there and actually look for them.
Great. Thanks, Cynthia. And I've been told we have time for one more question. And so to wrap things up, Cynthia, this question's for you. Surety from YouTube would like to know, if Europa does indeed have an ocean, what kind of things do you think we'll find there?
That's a great question. Let's see if we can go forward to slide, I think it's slide 32, please. The one that says ingredients for life. So one of the really cool things about Europa's ocean is that at the bottom of that ocean, there's a layer of rock. And in this rock layer, it's possible there could be hydrothermal vents. And on Earth, at the bottom of Earth's oceans, we have these hydrothermal vents. And most of the bottom of Earth's ocean, it's kind of boring, right? It's just kind of dusty and dirty, and there's not all that much going on there. But if you're in a submarine and you're down at the bottom of Earth's ocean, and then you come across one of these hydrothermal vents, these are the kinds of things you see over on the right. Now, this is a real video, but it's of Earth's ocean. This is not Europa's ocean. Maybe someday we'll get to go there. Maybe my kids or maybe my kids' kids will actually get to see pictures from the bottom of Europa's ocean. And boy, I wish they looked like this. But here at the bottom of Earth's oceans, we see these just abundant ecosystems. We see these places, they're like oases for life at the bottom of Earth's oceans. And they're basically using the thermal energy. So that the fluids, the bottom of Earth's ocean circulates through the crust and it gets heated up. And so you get all of these great chemical materials that can serve as food for an ecosystem. And you just find these abundant life forms. And so I think if there's life in Europa's ocean, maybe it could exist in one of these places.
That's a great question to end on. That is all the time that we have for tonight. If you have more questions about Jupiter or Europa, you can follow these websites, which they're going to put at the bottom of the screen. You can go there and see each of these missions, and there's all sorts of information and images and multimedia that you can learn, but keep asking those questions. Please join us next month for our Talk Science and Art, Picturing Discovery with Dr. Morgan Cable and visual strategist Joby Harris. I'd like to thank our speakers, Dr. Cynthia and Steve, for their exuberance and their knowledge. Thank you to Lindsay and everyone behind the scenes who make all this possible. And finally, a big thank you to all of you tonight who ask questions, who come and join us every month and watch this. As we keep saying, it is your space program, so thank you for joining us. Stay safe, stay kind, and we'll see you in July.